All right. It's working? Yeah, thanks. Thanks, William, for the awesome introduction and not setting the bar too high. My name is Stefan van Gastel, and I'm here with my colleague John Stroosnijder, and we are from the Dutch Ministry of Defense. Small disclaimer up front. We are going to talk about possible future developments that we're already researching and testing. At times, we will be deliberately vague and incomplete for obvious reasons. Moving on. Before we get into the nerdy candy, I want to briefly take you to the context, background, and rationale for this story. The Dutch Ministry of Defense, or MOD for short, is a diverse and versatile organization. We focus on high-tech and low labor intensiveness. We're a small country, but we have an air force, army, navy, and what we call marechaussee. There's no English translation for the latter, but think of it as, amongst other tasks, a military, police, and security force. And with these armed forces, we cover land, sea, air, space, and cyber domains. Three primary tasks of the MOD are defending our national territory and that of our allies, enforcing the national and international rule of law, and finally, providing assistance during crises and disasters. And we're also not spared modern-day threats and subsequent problems. A volatile geopolitical situation, don't have to tell anything about that. Increasing cyber attacks and influencing and unpredictable natural threats are just some examples. And in addition, we must look for answers for problems such as hybrid warfare, a shortage of personnel, and the risk of drowning in the sea of information. And with that current state clearly defined, let's direct our attention to achieving a desired state. And a set of principles has already been drawn. And for our efforts, we're going to discuss today, we are addressing the goals of information superiority, multi-domain and integrated operations, and being able to deploy both software, hardware, and personnel quickly, scalable, and self-supporting. And with that, we also have a vision of our desired state. Our IT innovation process or approach is pretty simple and really boils down to three distinct steps. First, we plan. We create a balance of free and problem-driven innovation proposals and ideas. And second, we experiment. So we actually research and experiment with new technologies, concepts, and material. We have the experts, like John, and skills to do a lot of it ourselves, but we also involve commercial entities for off-the-shelf solutions or additional knowledge. And finally, we try to deliver. So we build and deliver a lot of it ourselves, a lot of it with industry and partners. So after successful experiment or experiment iterations, we work closely with our IT production departments to smoothly transfer experiments to production.
We are talking about the edge. Kubernetes on the edge, some other compute factors on the edge. But first, let's take a little bit more look at what we perceive as the edge, because our edge may not be your edge, or maybe we have a lot of edges and some of them resemble yours, others maybe not. So, of course, we have our static data centers. Like every large company, we have those. Ours are well protected, so there's nothing special there, basically. And we have a lot of decentralized locations, because the Ministry of Defense doesn't just operate in these main locations. We also go abroad. We have locations in the Caribbean area. We have some people in embassies around the world. So we have a lot of decentralized edge locations. But it doesn't stop there. There's more. We also have our deployed edges. So when the Ministry of Defense needs to go somewhere for peacekeeping missions, for instance, we need to take our IT equipment with us. So those are our deployed edges. That can be everywhere in the world. But it doesn't stop there. There's even more. We also have mobile edges, things that are moving around, like ships, vehicles, and they're out in the field or in the middle of the ocean, and they need some compute capacity on board, and they need communication with our main data centers in the Netherlands. But we're still not done. There's even more. So another layer of our edge is our dismounted edge. This is where we're basically the new phase in which our soldiers individually will have IT and communication equipment basically in a backpack out in the field. So they're like a sort of mobile walking edge. And then when you think we're done, we have one more. We have the unmanned and the IoT layer. So there's a lot of unmanned system development going on. So we're also into developing this. So we also have unmanned systems, and we have all sorts of sensors everywhere around the world deployed, giving us information about what's going on. So this is a very broad spectrum of all sorts of edges. And with all these edges, there's complexity. Basically, everything that's in the static side in our data centers is relatively easy. We all know how it works, or how it should work. But when you go farther to the edge, to the far side of the edge, things get really, really complicated. And there's a lot of issues with power, with the ease of use, because not everybody running around in the field is an IT specialist. So things need to be very, very easy, and they just need to work. So this is basically what we're looking at from the MOD's perspective when we talk about the edge. There's not one type of edge, there's a lot. This is just one of the examples. This is a main headquarters that can be deployed abroad when there's a large mission. It consists of a lot of trucks, tents, and IT equipment within all those vehicles. This is very static. You set it up. It takes like 2 or 3 weeks, but then you have your edge data center where you like it. This is another example, a pretty one, if I may say so. This is one of our ships, and these ships are packed with IT equipment. So this is a floating naval edge system. We also have these kinds of vehicles equipped with all sorts of antennas and communication equipment and some edge equipment on board. They're driving around in the field, basically a mobile communications hub, and they serve out some small applications to the dismounted soldiers in the field. And these are our building blocks nowadays. So one of these trucks contains a lot of IT equipment. We just drive them into the area where we want them. And we always say one is none. So most of the time we like 2 or 4 trucks with IT equipment, communications equipment with them. And then we have our edge everywhere we can drive to, basically. But yeah, like I mentioned, when you go to the edge, things get difficult. So we have a lot of challenges. So this illustrates some of our challenges. And I'll get into a little bit more detail about what kind of challenges we are facing. So the first one here is that we, as the MOD, need to be the last IT standing. When everything breaks down, we need to be there to help. And we can only do that if our IT equipment is working. In order to do that, we can't always take these large, bulky equipment in trucks with us. So everything we do needs to be light, needs to be easy, needs to be low on power, and it needs to be able to handle like harsh weather, warm, cold, wet, but also sometimes, even I do that, I drop something. So it needs to be very ruggedized. It needs to be strong and durable. And then where we go, there's probably an issue, and it doesn't always need to mean that there's a conflict. It can also be like a natural disaster, like here on Sint Maarten. Everything is down, there's no power, there's no communication, no cell phone reception, nothing works. So we always need connectivity, we need to bring that with us, and it always needs to work. And then when we're somewhere and we are up and running, then there's always the threat of from the cyber space. So people either jamming our signals or trying to hack into our systems. Yeah, that's a real big issue. So we need to be aware of that, and we need to resist those kinds of attacks. And then there's the deployment. We need to be able to be out in an area really, really fast. So that should be done in like hours or maybe days, not weeks or months. And with all that, of course, we're the IT department, so we're going to talk about IT too. We need to support a whole lot of workloads. I can't just say we're going to run everything on Kubernetes. I can't just say I'm going to run everything on Linux or Windows. I probably need all of them. I need virtual machines, I need Docker containers, I need Kubernetes running. I need them all. So that makes things complicated because it still needs to be easy to use. So in the past, how we approach this, for all the Dutch people, they know this. This is the kaasgaaf methode. No way how to translate it to English. Any suggestions, welcome after the presentation. But we just take a little bit off the top, try to make things smaller. So instead of a big server, we use a little bit smaller server, a little bit smaller switch. Maybe if we have 2 switches, well, just take 1, because otherwise it will be too heavy. So we basically keep bringing things down a little bit until there's a point where we can't go any further. And then we're stuck. So that's our old approach. And we still have some big, bulky edge systems remaining. It doesn't get that small. So our new approach needs to be different. And this illustrates our new approach. We need something that's small, but very versatile, with a lot of options, a lot of features that we can use when we need it. So it needs to be something more like this multi-tool to explain where we're going to. It needs to be very, very versatile. So we started searching for a solution. And first of all, we were looking at the hardware, because basically choosing a little smaller model of a server or a switch, that doesn't work. So we took our research, we came up with some of these vendors. We could of course use like 20 Raspberry Pis or something, but they will probably break somewhere in the desert or on the North Pole. So we needed to do some more research into ruggedized hardware, and we came up with these kinds of equipment. Everybody here in the room can buy this stuff. This is not military grade, so this is available on the market. So we decided to use these components. Then there's communication. That's a real big issue. I didn't bring any of this stuff with me because I have to carry it all the way through the parking lot. It's a little bit too bulky. But still there are some smaller developments on the communication part, and basically the low Earth orbit satellite solutions. And the best known one is Starlink from SpaceX, from Mr. Musk. But there are some competitive products coming on the market that better suit the needs of the Ministry of Defense. And that will be a big game changer for our edge deployments. Basically, these are satellite systems weighing like 5 to 10 kilos. You can take them with them. And it doesn't matter where you are, in the middle of the ocean, middle of the desert, on the North Pole, on the South Pole, on an island where there's been a hurricane. If you set this up, 5 minutes later, you have brilliant connectivity. So that's great. And then we need to reduce the complexity of it all. So it can't be difficult. We can't send like 20 IT specialists into a disaster area. That doesn't work. So we try to make things easier, and we try to automate everything as much as we can. And also security. Well, basically on security, we won't make any compromises. We've always been very focused on security, so we will keep on focusing on security. The only thing that we will be doing is looking ahead. So what will be changing in the future? How can we easily adapt our solution to new security situations using less hardware, smarter software, more automation. So that's how we approach our security. Not a lot of compromises there, basically none. And for the multiple workloads, yeah, some people say, oh, you should leave the virtual machines behind, go to containers all the way. For a lot of our applications, that won't work yet. So we need a mix of virtual machines and containers running either on a Linux host with, for instance, Docker or on Kubernetes. So we have that now ready. This is working just fine. We can accommodate all these workloads together on one piece of hardware. And our vision to do this is that we will build it just like Lego. So we will just stack up the blocks, and if something needs to change in one of these blocks, we can change them easily. So we start out with our low swap hardware, a hypervisor, add a crypto, some internet connectivity, some fancy virtual routing stuff to connect to our network, and then we can have all our workloads running. And basically the kit that we have right now, there is even a smaller option than this one, but this is the kit right here. If someone wants to look at it, because in the back you probably can't really see it, please walk forward after the session. I can explain a little bit about it. But this is basically all we need to bring along to get our connectivity up and running, and maybe a satellite dish with that. And if something changes, for instance, we need a better crypto because our cyber threats are increasing, we'll just rip it out and replace it with something new. So everything we've done in this block that's over here is changeable. And in the future, we can probably add some new things. for instance, some local LTE mobile services, or we can add some VoIP bridges so everybody can talk with radios to telephones, etc., and vice versa. So we're looking into those options too. But yeah, okay, this all works on paper, so fine. But of course we need to test it. That's the fun part of my job. I need to go out and test stuff. So this is basically 2 years ago, the first Starlink dish that was available. We tested that. We were instantly in love with it. Not so much with the company, but well, with the technology. And then we added our hardware kit. This is a different type of hardware that we tested. And then we went along. Some of my military colleagues, we went along to an exercise in Germany, and we tested it for like 3 or 4 weeks. And they were also in love with it, so they didn't want to give it back to me. But yeah, I had only one prototype, so I had to be tough on them. I took it back. But now we're building new ones for them, so I think they will be happy soon. But we had a gap in our vision, because if we want to deploy this in a disaster situation, we need something very simple: power, electricity. So if we go somewhere where there was a hurricane and everything is broken, then that's a big issue. Of course, we can take a generator and a bunch of gallons of fuel. That will work, and that's not a bad solution from a military point of view. But maybe we can build it a little bit smarter. So maybe we can add a battery. Maybe we can add solar and wind power. Maybe we can do something with biofuel, so a little bit more green. So in the end, we decided, okay, let's do a approach with two solutions. First of all, just take a portable generator with us. That's the quick and dirty solution, and put all the hardware in small cases that you can just bring along. And you need, like, with 2 people and 3 cases, you're done. The other solution is to build it into an electric emergency response vehicle. That's a project we're doing with a Dutch company. And this is basically what we're building right now. So we have this vehicle, which is fully electrically driven, powered, and we can add a range extender, which is basically a generator, for some extra power or extra range. And then we'll just build all this hardware, basically like a car stereo, into the dashboard. And then we have our edge data center in this vehicle. We will add some extra batteries, some solar panels, maybe some wind energy, that's called a flower turbine. It's a pretty turbine that we can just put down, and when we're somewhere where there's a lot of wind, we can just put them up and we have wind power. And of course, a satellite dish on the roof. And that will be the complete package for the emergency response vehicle. And this one will actually fit into a Chinook helicopter, or can be hung underneath the helicopter and be transported to any location we like. So this is what we're working on. This will be finished in 2024. So maybe somewhere next year we can demonstrate it. Right now we have the vehicle, we have the equipment, but not together. So also this needs to be experimented, of course. So here is the actual vehicle. The solar power and batteries have been tested. All the end user equipment, because yeah, it's fun to have a computing kit with you, but if nobody has a laptop or a system to use it, that doesn't work. So we've all been experimenting with this too. Like I said before, this is really, really the fun part of my job. So, yeah. That being said, Stefan will take over now.
That being said, some of you might be wondering, so where does Kubernetes fit in all of this? So let's fast forward to the future, or near future, next year, right? John just described for us. Together with the TNO Research Institute, we completed the first exploratory research programs regarding future command and control systems and the technologies required to run those systems. And this resulted in embracing cloud-native technology and Kubernetes as a platform for these future technologies and future command and control systems. So, if you're interested in a more in-depth talk about what I'm about to share with you, just Google the title of this slide, and you'll find a KubeCon talk Anna Kosek and I gave at KubeCon this year in Amsterdam. Because I'm just going to touch the surface of this. But let's start at the beginning. Given the situation John just left us in, the simplified image on the right depicts some edge vehicles with some autonomous or semi-autonomous controlled drones running potentially local clusters for their command and control systems. This could be sufficient, but we don't need much imagination to come up with some situations in which this is not. For example, in a combined and potentially multi-domain, so land, sea, air, space, cyber, operation where ad hoc connections, interoperability, and data synchronization are required, we need a solution that meets these requirements. Imagine a constellation of vehicles, like the picture is showing, and dismounted troops that can have their on-board systems or clusters, or on-person system or clusters, join or leave a federation of clusters, synchronize data, and run standalone if connectivity is lost. And where, upon returning to, for example, a compound, data can be offloaded and new software or new AI models can be trained or loaded into or deployed to the vehicles again. And in the research program I mentioned earlier, we researched what is the state of the art regarding Kubernetes, multi-cluster topologies, cluster federation, and scheduling using custom telemetry. And to achieve this, we found some nice ingredients to throw into the mix. Obviously, Kubernetes as our envisioned target platform for future composable command and control applications and supporting services. Next, we found that Lyco, a solution for seamless Kubernetes multi-cluster topologies supporting heterogeneous on-premise, cloud, and edge infrastructures. Could fit our need. Also, OLSR, which stands for Optimized Link State Routing Protocol. This is a routing protocol that exposes a cost metric based on bandwidth, latency, and packet loss, and exposes this metric to the operating system. And finally, to make scheduling decisions based on this cost metric, we used Intel TAS, Telemetry Aware Scheduling. And what should this look like in real life? Well, here we have a cluster A, which could be, for example, a compound that has big computational resources. It has no data source to observe its environment, and therefore it's going to search for a camera or a surveillance functionality in a specific area. We have two camera systems here, cluster B and cluster C, which could be, for example, a Reaper drone like you saw in the introduction video, or maybe one of the vehicles John showed you, which has a camera system. But which one to choose? At this moment in time, cluster B has the better network connection. So it chooses cluster B to deploy the software to. So we can read the camera. And because we don't know, it's an edge situation, so we don't know what connectivity is going to be like in the future, let's make it a stateful applications, because who knows how long we can keep this great connection. And there it goes. Cluster B's scanning pattern, for example, took it away from cluster A, and the connection is lost, which is a bummer, but wait, it's a stateful application, so it's still running on the local cluster, cluster B, for example, that Reaper drone cluster, and the application is running there, so it's still storing its local data. Now, the federated cluster, or the cluster federation, just got smaller, but it's time for cluster A to decide, will cluster B be back on time? And how long should it wait? And how long is too long? Should cluster A reschedule to the new cluster, for example, C? We want cluster A to allow cluster B to be away for a bit of time. If time's up, A can reschedule to C. If B comes back in time, we want the offline portion of the data streamed back to the A cluster and streaming to resume. Not so high expectations, totally reasonable and quite useful tactical edge functionality. To finally show you a demo of what this looks like, I'm going to show you a recorded video from the perspective of a single vehicle called Cluster 0. I don't know if it's very visible, but the large purple/blue dot is Cluster 0. On the bottom, we will see a timeline of different clusters. There are going to be more, spoiler alert. And on the top right, you will see a graph of network cost between different clusters. So, for example, the situation I just described, a compound with with a Reaper or a different vehicle, or between 3 different vehicles. All right, starting all systems. So, we are going to see cluster 1 and 2, here they come, join the federation. So they are connected. And we will also see that resources from cluster 1 and 2 are visible as virtual kubelets in cluster 0. And in the graph on the top right, and between the nodes, we can see the network costs, which are 214 at the moment. Now, let's apply let's deploy an application which runs both locally and remote, so both in cluster 0 and in cluster 1, and start transferring data, which should be there in a second. So here you can see the locally deployed application and the remote deployed application, and we can see data being transferred. Network costs are both approximately the same, and we're applying network effects. So you can see that network costs between cluster 1 and 0 are rising to 428 because it's just lost its connection. But the application is not being rescheduled because we extended the unjoining period, and Kubernetes and the scheduler are just waiting this unjoining period for the application to get back. So let's wait for that. Hope I timed it well. And there it is. So connection is back, and we should see connection cost between 0 and 1 dropping from 450 to less. And streaming being resumed. This shows how this would work. We've tested this with actual vehicles in a test environment. We've tested this in a lab environment. And with that, I'm going to conclude our talk. So, in summary, we've discussed what our edges look like, what all of our different use cases are, what the situations are we need to take in account, what our challenges are, how we used the Kaasgaaf method in the past and are looking for new methods to bring extra functionality to our edge situations. What cool developments we're having with the electric buggy, with the electric quad, making it autonomous data centers at our edge situations, and how we use Kubernetes and other technologies to explore the possibilities of our future military edges. And that's it for us. Thank you.